this is the basic. You've probably done that before. I will say for this class, you may not always be able to try all possible hyperparameters, but for a paper, if you decide to take your work and submit to a conference, I highly suggest to go and take the time to do all this. For the class, you have limited GPUs, and so we are not going to be picky about the hyperparameters as much, but that's something to be aware for, definitely for a paper. And I want to share like the methodology. For most of you, you hopefully will be lucky and your data set already have a specified test set, specified validation set, and a training set. And so this is great because if you have a lot of data, this is the way to go. It's nice because then people can easily replicate your results. If you want to be very adventurous, then you can go ahead and make this a test set like separate from a challenge. But for some of you, maybe in effective computing data sets and others, you may have not enough data. And what you will do is then, instead of have a dedicated test set, you just take your whole data set, take maybe 1/10 of the data set, call it the test set, and use 9/10 as training and validation, do all of your process, and then repeat it 10 times. And the extreme version would be leave one out, like leave one person out or one video out. Okay, I want to emphasize one thing here is that like linear classifier, I will again go a little bit faster on this, but what I want to talk here is the idea of, because this is just an introduction to neural network. I could have called this just neural network these days, but I don't know. For me, it's a linear classifier. A neuron is a lot like a linear classifier, so with a simple nonlinearity activation at the end. But at the core of a neuron, the core part is really a linear classifier. You could imagine when I'm asking myself, like, is it a dog or not? I could imagine take that whole image, make it a vector, and then use only one neuron. I know that's quite crazy, but yeah, imagine that's called one neuron. By the way, one neuron is called a linear classifier. Okay, depending on which activation function, it will be maybe slightly different from a linear classifier, but it will be in the same family. And what are the three main parts of almost any classifier, but specifically linear classifiers and neural networks? Three tasks when you think about learning classifier. One is defining your score function, and we'll discuss that in a minute. And for a lot of neural networks, because you select specific type of neurons, and then you kind of bypassing that design question. But I'd like you to at least be aware that underneath there is that happening. The one that is important for almost any model is the loss function. You need to define what are you penalizing, what is it that you're penalizing, what kind of situation you want to penalize. And then you need to go from maybe a model that you initialize randomly, in this case maybe this one neuron that you have, and it has a bunch of weights, and you may be initializing randomly. You want to start from that random position in the space of your model, parameter space, to get to that, hopefully, to that global optima that really gives you the best possible classification. And that's called optimization, that walking through the space. And I think the intuition of walking is really good in this case. So the score function, this is something that is happening in any neural network, but we don't realize it, and I want you to take at least a moment to think about it. When you have the image and then you have all these class labels, the score function is, what it answers is, what should be the prediction score for each class label, okay? So if you have, for example, you have the image, and it has the possibility of a dog, it has a possibility of a cat, a dog, a pig. The idea here is I want to have a score for each of these labels. And the way to do it will be, maybe the simplest one will be to have one neuron, and in this naming will be one classifier, linear classifier for each of them. You'll have one neuron for duck, one neuron for cat, one neuron for dog, and one for pig and bird. And a neuron at its simplest, with a linear activation function, a neuron with a linear activation is this exact function. And so X, as you remember, is a vector usually. And I say WI because if it's a training set, I may have many of these images. And then you have W, which is the same W, or the weight, for all my samples. That's what I'm trying to learn. And I'm also trying to learn the bias as well. And we will explain visually what the bias can be interpreted as well. But these are the two sets of parameters that I will learn. And what this function is this one value that tells you how much is it, how you score. So you could score it for a duck, score it for a cat, score it for a dog, for each of them. I want to give an example with numbers. So if it is 3072, because it's an image of 32 by 32 by 3, this is a very long vector, then the weight will be, let's say that I have 10 of these classes, then it's going to be 10 times 3072. I have only a bias for each class, or only one bias per class, and these are going to be my parameters together. Okay, so this is the idea for the, and the number of class is the number of scores will be the number of classes. And so the W, what it does is give you the direction of the slope of the linear classification, and the beta. The bias is there to give you the distance to it. So the distance, and then the W gives you the slope. So this is just basic linear classifier. You've seen it many times. I just want to help you with like naming convention, because it gets very confusing. You rarely see nicely written like this. In fact, most of the time, if you're lucky, you will get to this, which what it means is that you took your bias and in fact added it just simply by making your input slightly longer by only adding 1 to it, and now you have all your parameters in one W. It's just cleaner. And so another nice thing you can do is, because you will have many classifiers, really you will have many sets of parameters. You will have one set of parameters for dog, for cat, for all of them. You could simply say I have a different function, or you could go very simple, very tight. And so these are all different ways of naming. These are all equivalent. This is just a notation. So I would love it if you always take the time to say, hey, what are my parameters? But a lot of time people will just take and maybe they will add here a simple thing, like they may take the time to have an X here, but that's maybe the only thing. But this is equivalent to this one as well. So if you have many classes, then you have many of these linear classifiers. In this case, what I show here is 3 neurons. 3 linear with linear activation. This is what you see here. But how do you get to optimization? If you want to optimize this, you have, let's say, 10 of these scores. But then I need to ask myself, now I have 10 of these scores. Given an image during training, I have 10 of these scores, and let's say I have 1,000 images. and let's say the real label is dog, and so I want and the scores right now, dog is high, cat is also quite high, and I want to congratulate my current weights to say, hey, you got it, perfect. Or maybe if it was the opposite and let's say dog was selected too high, I would like to say, no, this is not correct. How can I go ahead and tell the algorithm this is not the right thing or this is the right thing? The loss function, in very simple term, is how to assign only one number represented how unhappy we are about these scores. Okay, so you get many different scores for each possible class, and then you have to ask yourself, like, how do I finally at the end of the day just give one number? And so and that's what the almost science of loss function comes in, and it's almost a science in itself to looking and deciding what loss function to use. So the loss function quantifies the amount by which the prediction score deviates from the actual values. That is what the key aspect is. So here, because these scores are very different, and I want to have a loss, maybe a loss that goes always from 0 to 1, how can I take all these scores and normalize it? And so there's very different ways, but probably the simplest one is using a logistic. I go from numbers that goes from minus infinity, and I want to normalize it from 0 to 1 or minus 1 to 1. What is the simplest function to that? This is a logistic function. It goes from minus infinity to plus infinity, and it can nicely give you a number from 0 to 1. So now I can take all of these scores and simply put them together. So this is the scores here, and if I have only one score and I want to normalize it, then I can use that logistic function in this case. If you have two of them, it's also quite simple because one is the opposite. Suppose that it's either a dog, or all your images are either dog or cat, or it's dog or no dog, for example. In this case, then it becomes a simple logistic regression, but this is the same equation. And so in this case, the true class in a logistic regression, like the 0 is seen as your decision boundary in this case. And this is what you see here. But if you have multiple class, then you just have a very nice, and now people use that like term softmax, not realizing what it does, but softmax, what it does, it's just a normalization. It just brings everything that could go from minus infinity to plus infinity to something between 0 and 1. And now, are there any parameters that are learned just in that? No, the loss function itself doesn't have parameters in it. The parameters are before the loss function. And we'll look at it in the neural network. But when you say I have a softmax layer in a neural network, softmax doesn't have parameters. It's just a normalization. So softmax is just there, and the softmax, what it does is just allows you to easily implement some other loss function. So now what I did with this softmax is I ended up taking all of my 10 different scores and normalizing them. So I get a vector instead of 10, but I can go ahead and normalize it. And once it's normalized, then you can look at the cross entropy. That softmax is there, and then you can look at this and take advantage, and then you minimize, in the case of a cross entropy, minimizing the negative log likelihood of it. And this is just a matrix version of that, that as an example of that, that you can look more in details in the slides, where you have your weights, you have your input and your beta, and you can see the different steps of it. One is you take the exponential of this, and then you go ahead and you can normalize this, and that's finally what gives you the log on that. So okay, this is one example of loss. I just want to give another one, and I know we're running a little bit out of time, so I'm gonna wrap up relatively soon. But the other one, which is under many names, but I like it quite a bit, is the hinge loss, and it definitely has been used and is used quite a bit these days in many different approaches. I will discuss more in a little bit, but here the idea is not just to look at the distance. It's not just normalizing and looking at the peak in this. In this case, what you will do is look at the difference between the correct class and the incorrect class. And the trick here is that because you sum over all the incorrect labels, really what you end up doing is like you end up penalizing mistakes. You ended up penalizing mistakes, and that's a trick because of the max. So what you want is, if it's correct, it's good. There's nothing here. I'm not, although you could change it, but it's okay. But if it's wrong, like how wrong it is it? And how wrong is it will be that margin that you want, and you would like that margin to be as large as possible. And one of the most famous use of that, at least it was famous back in the days, was support vector machines. Contrastive learning has a flavor of that as well. So there is one little kind of hyperparameters, but this one often doesn't matter as much. But it's this delta to allow you to get a bond, some kind of buffer into this. So these are two losses. There will be more during the class. I just wanted, but a loss in general has three main parts, okay, to it. One is the data part. This is the main thing we discuss about. The data part, the data term. How much is my data matching my expectations? That's kind of the loss that I talked to you about. And we talk about different versions of that. But there's also two different components to that can be added. One is regularization. Regularization is often there to prevent the model to becoming too complex. You will often add this regularization. This is in almost every model that you would get some level of regularization, primarily because in the perfect world, you have infinite amount of data, and probably you could be a lot simpler in your regularization. But a lot of time you have example that may not have never been in the test set, and so you want to be able to generalize to them, and at the same time keeping the complexity of your model simpler. So it's either for smoothness, so there's very interesting. And the lambda, you ask yourself, it is a hyperparameter. That's another example of these hyperparameters. And there's something that we'll discuss a little bit later. Sometimes you will also have in your optimization some constraints. You don't want certain parameters to go larger than a certain threshold. You will have some constraints. This is not often, but it does. Why is it not so often? It becomes a problem for optimization. Like the more constraints you have, the optimization becomes more complex. Often for the regularization these days, people have managed to find very interesting ways of regularizing and still being able to get a gradient. Sometimes with the constraints, you get some nonlinearity or some other things that makes a typical gradient-based optimization a lot more challenging. So we'll discuss more on Thursday, the core of this, which is on the neural network, where at the end, I'm just going to give you 1 or 2 slides, and we'll discuss more, a few slides, but we'll discuss more on Thursday, just a teaser. But neurons, what they are linear classifiers. And that's really the core of it. You see exactly the same linear classifier. So a neuron is a linear classifier, but there's an activation function to know like how, but and the activation allows you to almost, some of them almost look like a on-off switch. And so what's great is that it allows you to say, and that's part of how the neurons will go, gather a bunch of evidence. You could imagine I gather a bunch of evidence, and then once you have enough evidence, then you activate, you pass that threshold. Now we use neurons, and a lot of these neurons don't even look like neurons, or at least nowhere close to what human neurons are. But at the basic, these were kind of a linear classifier with an activation function. You will, when we think of neural network, the simplest one, the multi-layer perceptron, each of these arrow, not each arrow, but if you set all of these arrows together, this is one neuron. So take all of these evidences from all of them and get one neuron and output from one neuron. That's, you could say, output of a neuron, response of a neuron. That's sometimes you could call them scores, but the scores will usually only be used at the end. When you talk about scores, you here have 3 scores. No, sorry, 4 scores maybe. Oh no, sorry, you have only 1 score. You have only 1 neuron at the end. But if you had many of these neurons, so here it's only dog or not. But if you had dog, cats, and something, you could have many of these at the end. So these will be scores. But here we'll talk about response or at the output of that. And so the building block of this is simply that linear classifier plus this activation function. And as you know, there's many of these activation functions. We, back in the days, were focusing primarily on these two, tanh and sigmoid. In fact, LSTM, which used to be very popular, long short-term memory, LSTM, which is a type of recurrent neural network. And what was really interesting is that, and we'll look at it when we look at the recurrent neural network, is tanh, the main thing was it nicely goes from -1 to 1, while the sigmoid goes from 0 to 1. And when you're building or designing these architectures, you may realize that having a positive and negative may help your learning. And so you will decide from a design perspective. So, and so multi-layer neural network simply is a recursive process. It's like, you could see it, you have one layer of neurons. So 1 neuron, 2 neurons, 3 neurons, 4 neurons. This is one layer, and that's what I show here. And so for this layer, I will learn a set of weights. What is it? Is I will learn a set of weight for neuron 1, a set of weight for neuron 2, set of weight on neuron 3. And so W is often seen almost as a matrix, or what's called also a 3D or 4D matrix, what's called a tensor. So this, when you hear the word tensor, you can do multidimensional matrix as one way to think of a tensor. So when I say W here, are all these neural parameters from the neural network. And so I have parameters for the first layer, parameters for a second layer, parameters for the third layers. And then here I could have many scores. In this case, I have only one output. So the score function here, the output here, what it is just it's just recurrence. Like it's just like from one out, and then the output of the one goes in the output of the other, and the output of the third one. And our loss function is over that output. So output here is only 1, and here if you have an Euclidean loss, all this. And loss, as you remember, is only one number that tells you how good or bad things. And so I'm gonna, I think this, well, yeah, this was my last sentence, last slide. When you do these, there is 2 terms I want you to one is inference. Inference, what it means is like feed forward, like moving through the network, like inference. Like inference is like I have X and I get my inference Y or my scores. So inference is use the score, or inference is both get the score and use them. And at that point, when you do inference, it should say use, compute the score here, and it should not say use. Compute the scores and use them. And that takes already learned parameters. And then at training, the training time is, that's where you use the loss function, and then you do optimization. And one way of doing optimization is gradient-based approach. And when you do this gradient-based approach, one thing you will realize is internally, you will do inference internally in that loop of optimization. You will often do some inference. But what you will do is for a specific set W at that time, at that iteration. So we'll discuss more there. So don't forget to do today your project preference form. That's everybody, all students. Tomorrow, also select in your reading group. Just be sure to select your go in your Google Sheet, your own study group, and select. Post your summary on Friday or before that. It's even better if you do before. Oh, I forgot to put on Thursday morning, be sure to have your highlights form. And then on Monday, do the discussion. So yeah, thank you very much for your attention.